Hello everyone, I'm Kefei Liu, a third-year PhD student at the Beijing University of Posts and Telecommunications. Today, I will introduce R-Pingmesh, a service-aware RoCE network monitoring and diagnostic system. Now, I will first introduce the characteristics of RoCE network problems. First, commodity RNICs use go-back-N as the retransmission mechanism. Therefore, ultimate throughput is sensitive to packet drops. Second, RoCE networks typically require a variety of configurations to ensure a lossless environment. This leads to a high probability of misconfigurations, which can cause packet drops and throughput degradation. Third, RNIC problems is frequent, such as RNIC flapping, which can lead to packet drops and throughput degradation. In addition, distributed machine learning has a barrier effect. In DML, all participating GPUs periodically synchronize their local gradients over the network. The completion time of this process is determined by the slowest GPU. Either RNIC or in-network packet drops can cause throughput degradation of multiple flows, which will further degrade the average throughput of the entire DML cluster. Recently, the size of large language models is increasing, and typical model parameters have now reached 100 billion or even larger than 1000 billion. To increase the training rate, the DML cluster uses more GPUs for training as well as more RNICs and switches to connect these GPUs. As a result, both the frequency and impact of network problems are increasing. Efficient troubleshooting is critical for optimal training performance. When training fails or training performance degrades, the problem needs to be quickly located. Large clusters that are idle for troubleshooting or running in unhealthy conditions can result in significant financial losses. However, our existing RoCE network monitoring and diagnostic methods are not efficient. First, we are hard to detect failures and performance bottlenecks when they occur due to the lack of an effective monitoring system. Second, our existing RoCE network troubleshooting methods could be roughly divided into two steps. Step 1. Inspect configurations, logs, and anomalous metrics. Step 2. Run benchmark tools in the cluster. This method is time-consuming for large clusters. In addition, when training fails or performance degrades, we are hard to tell if the problem is in the network. One of the most common service failure is nickel communication timeout. This sounds like a network problem. However, the cause could also be a remote process exit due to GPU error, which is not a network problem. Another case is degraded training throughput. The cause seems like a network problem, such as network congestion. However, the root cause may be bugs in the training code. The truth is that we often waste time trying to find the root cause of non-network problems in the network. We need an efficient RoCE network monitoring and diagnostic system. It can quickly detect and locate RoCE network failures and performance bottlenecks. In addition, it can quickly determine if the network is to blame when service performance degrades. We are inspired by our TCP networks. Pingmesh is a data center physical and TCP network monitoring and diagnostic system. Pingmesh agent has been deployed on most of the servers in our data centers. If we can extend Pingmesh to RoCE networks, we can then build on existing systems with minimal effort. However, deploying Pingmesh directly in RoCE networks cannot meet our requirements. In this section, we present our targets and show the limitations of Pingmesh. First, we need to detect problems specific to RoCE networks. TCP probes in Pingmesh cannot detect all problems in the RoCE queue. Second, the RNIC and switch packet drops can interfere with each other during troubleshooting. we need to distinguish between RNIC and in-network drops in order to accurately locate RNIC and switch problems. However, Pingmesh cannot identify the location of packet drops. Third, to detect and locate performance bottlenecks, we need to accurately measure the end-host processing delay and the RTT of the passes used by the service. However, Pingmesh measures RTT as a software layer, although Pingmesh can detect an abnormal increase in RTT when bottleneck occurs. It is difficult to locate them because the increase can come from either end hosts or networks. As shown in this figure, the software RTT measured by Pingmesh fluctuates as the host average load changes. Finally, not all detected problems should be resolved immediately. Some problems do not severely affect services. Fixing them may also cause service performance degradation. We need to prioritize each detected problem based on its impact. The priority also helps determine if a service problem is caused by the network. If no P0 or P1 problems are detected when service performance degrades, the network is innocent. However, Pingmesh cannot assess the impact of problems on service. Next, we introduce the design of R-Pingmesh. Similar to the architecture in Pingmesh, R-Pingmesh still has three components: controller, agent, and analyzer. In terms of functions, R-Pingmesh has two independent functions. The first is cluster network monitoring. It constructs RoCE packets to probe between all RNICs in a RoCE cluster. It is service independent and can detect network problems before service run. The second is service tracing probing. Service tracing probes passes used by services. In this way, it can assess the impact of detected problems on services. Next, we introduce each component of R-Pingmesh. For controller, it has two core missions. The first mission is to store the latest communication information of each RNIC, including GID and QPN. The second mission is to create TOR mesh pin list and inter-TOR pin list for each RNIC. In cluster monitoring, TOR mesh is to probe within TOR switches and monitor RNIC status, while inter-TOR probing is to cover all network links between different TOR switches. For agent, we first introduce how to measure RTT and processing delay. A critical consideration is the choice of QP type. We compare the features of all three QP types in the table. In terms of accurate measurement, we need to get 6 timestamps as shown in the figure, and we can then use this listed formula to calculate network RTT and processing delay. Commodity RNIC provides an RNIC timestamp when generating cookie, and all three QP types can get timestamps 3 and 5 from received cookies. However, only UC and UD can obtain timestamp 2 and 4. In terms of connection overhead, with RC and UC, the local RNIC must create a QP for each target RNIC, which consumes a limited QP context cache in the RNIC. With UD, agent only needs to create one QP on each RNIC, which has very low connection overhead. Therefore, agent uses UD for active probing, which can accurately measure RTT and processing delay with low connection overhead. Due to time limits, here we present some probing process highlights. First, timestamp 4 can only be obtained after the first ACK is sent. Therefore, the responder needs to send the second ACK to carry 4-3. Second, all duration calculations do not require clock synchronization. The second mission of agent is monitor and probe the 5 tuples of service flows. Agent uses eBPF to trace the core to the kernel functions modify QP and destroy QP. By tracing these two verbs, agent can keep the 5 tuple used by services in real time. Then, agent will construct probes with the same 5 tuple as the service flows. In this way, these probes can cover the exact network passes used by the service due to ECMP hashing. For path tracing, agent periodically trace through the latest passes of probe packets and their eggs. This tracing method is easy to deploy. Continuous path tracing allows an analyzer to accurately locate network problems immediately as they occur. Next, we introduce the data analyzer. Among all the data uploaded by agent, packet drops could be attributed to RNICs or switches. And a key task of analyzer is to distinguish between RNIC and in-network drops. If we can detect anomalous RNICs, we can filter out anomalous probes caused by RNICs and use switch drops to accurately locate switch network problems. We use TR-Mesh to do this. Our experience is to introduce minimal uncertainty. TR-Mesh probing involves only 2 links. If a probe from RNIC A to RNIC B shows anomalies, the problem is either at A, B, or the TR switch. If many probes to an RNIC show anomalies at the same time, that RNIC is probably abnormal. After filtering out RNIC drops, we can get anomalous probes caused only by switches. The analyzer uses a simple voting algorithm to infer abnormal devices. It traverses the passes of these probes and their eggs, and counts the number of times each link or switch is traversed. The link or switch with the highest number of votes is the most suspicious. The final mission for analyzer is to assess the impact of problems on services. If a problem is detected by service tracing, the problem can affect the service. In these problems, if the service performance degradation exceeds the preset threshold, this problem is P0. Otherwise, this problem is P1. If a problem is detected by cluster monitoring but not by service tracing, this problem is outside the service network. Note that if service performance degrades, but service tracing does not find any problem, then the service network is innocent. Next, we will show the performance of R-Pingmesh. We have deployed R-Pingmesh for over 6 months on tens of thousands of RNICs. We evaluate R-Pingmesh in a large DML RoCE cluster. It has 3 tiers of switches to accommodate thousands of GPU servers. As shown in the upper figure, during checkpoints, the RoCE network is briefly idle. In addition, there are 2 anomalous throughput degradations. At the same time, the network RTT measured by service tracing also decreases. This shows that R-Pingmesh can accurately measure latency metrics and use them to reflect service status. For the 2 anomalous throughput degradation, service tracing quickly detects 2 severe packet drops on switches, which confirms that both degradations are caused by packet drops in the service network. In addition, during this time, cluster monitoring detects an anomalous RNIC that continues to drop packets. However, service tracing does not see any RNIC drops. Therefore, we conclude that the problem is outside the service network. In another case, the service tracing rate and average throughput continues to decrease, and our service team suspects that the network is congested. We then check the metrics in R-Pingmesh. As shown in the figure, the RTT is also decreasing, and the processing delay is stable, proving that there is no bottleneck in network or CPU processing. As shown in this table, during deployment, R-Pingmesh efficiently detects and locates 14 types of problems caused by hardware failures, misconfigurations, network congestion, and intra-host bottlenecks. Next, we present some of learned experiences. First, we can use the measured tail RTT to reflect network congestion, as the RTT measured by R-Pingmesh is accurate. Our DML services typically use 2 communication modes. all reduce, and all-to-all. In the left figure, we can see that all reduce is less congested, and all-to-all can cause severe congestion. In the right figure, compared with DCQCN, our self-developed congestion control algorithm can effectively reduce the tail RTT in all-to-all. From all the network congestion detected by R-Pingmesh, two causes are the most common. The first is 2R switch downlink congestion caused by man-to-1 encasting, which should be alleviated by tuning congestion control parameters or design better congestion control algorithms. The second is 2R switch uplink congestion caused by ECMP hash collision, which can be avoided or mitigated by designing better load balancing algorithms. The framework of R-Pingmesh ensures that it can adapt to any network topology. In practice, we can leverage the feature of network topology to improve the system design. For example, in real optimized clusters, probes between RNICs on a host traverse the top-tier switches in the cluster. Therefore, we can have RNICs on a host probe each other to cover all network links. In this way, agent does not need to rely on controller to get pin lists. Furthermore, agent can detect one-way timeout and measure one-way delay. With one-way probe data, we can locate network problems more accurately. In conclusion, we propose R-Pingmesh, a RoCE network monitoring and diagnostic system. R-Pingmesh can be easily deployed with low overhead. It can detect and locate failures and bottlenecks in networks and end hosts. In addition, it can determine if a problem is network and assess its impact on services. That's all for my present. Thank you very much.